Hello, folks. This is the first lecture after the summer break and week 7, lecture 1. And a new phase of the course is going to begin. The first 6 weeks dealt with finite element analysis with the CATIA program. Now we're going to do mechanism design with CATIA program. They're unrelated, so and the final exam will be covering only this part of the course. Now, on the agenda today, I want to discuss, first of all, some of the things that come up in mechanism design, and the items are listed here. And we go through it as I describe the problem later on. First of all, if you're following the textbook, we are switching. This is the mechanism design textbook. And let me remind you what mechanisms were. You discussed this thing in the third year course, machine dynamics, and essentially we are going to replicate what was done there, except that the only kinematic aspects are going to be considered. Okay, so we are only interested in the position, velocity, and acceleration of rigid bodies or things associated with rigid bodies. So it all goes, this business of mechanism goes back to the beginning of engineering, really. Okay. Uh, just to remind you that a mechanism is consisting of several parts, or let me refer to them as bodies, but this is a bad choice of wording because body means something else in CATIA, but the several parts or links that are attached together or joined together through joints, which are also known as kinematic pairs, and the motion of uh, these parts are of interest to us. So a mechanism is made of bodies and joints, okay, or links and kinematic pairs slash joints. There can be flexible mechanisms too. We are going to assume that each body or each part that makes these things are entirely rigid. There are also flexible mechanisms such as chains and belts and things like that that we're not interested right now. Now, mechanisms, their sole purpose is to translate motion and forces. Okay, let me give you some examples of mechanisms. For example, slider crank mechanism up there, which is the essential component in an internal combustion engine. We have a Geneva mechanism that's shown on the right. Each of these are made of several parts. And for example, in the slider crank mechanism, part 1, part 2, part 3, and part 4, the ground, a 4-bar linkage, which essentially a wiper blade is wiper mechanism is made of. Okay, and here is a earth mover bulldozer that is basically 4-bar linkage. Okay, now when it comes to joints, uh, these are the ones that we're going to be discussing in this course. There are spherical joint, revolute joint, cylindrical, prismatic, planar, and this is also some version of that, and also universal joint. And there may be a couple more that we're going to discuss throughout the course. But the first one that we're going to talk about is the simplest one, essentially, that we can come up with is uh, planar or prismatic joints. So suppose that we have this body, rigid body, which you know from your uh, machine dynamics has 6 degrees of freedom, or dynamics course, you have 6 degrees of freedoms, 3 translations and 3 rotations. If I take this block and put it on that plane, notice that it can translate in direction X, direction Y, and rotate about this vertical axis, which is direction Z. So a planar joint that you see here, this is called a joint. A joint has been created. A joint is an interaction between two parts basically, or two bodies. This has 3 degrees of freedom, two translation, one rotation. Now, if I insist that this edge travels along that edge, then the only degree of freedom that you have is motion in X direction, or on this direction, whatever it happens to be, whether it's X or Y or Z, it doesn't matter. So this becomes a single degree of freedom. So notice that a planar joint is made effectively by saying that the bottom of this is in contact with the stays in contact with the top of that plate, and a prismatic joint is, of course, a special case of a planar joint where the edges also move along the same line. So, for example, in the case of prismatic joint, you have to have a, a contact between two faces, contact or coincidence between two faces, the bottom of the block and the top of the ground, and the edge of the block and the edge of this plate. So two planes and two straight lines. That's what a prismatic joint is. So the first problem that we're going to be doing is a block that is traveling along that longer path. That longer path is stationary, but this block is traveling along that. So obviously we are dealing with a prismatic joint. And the dimensions are given here, but those are not critical. However, these are dimension, and we want to give this thing some physics interpretation. For example, suppose we were told that the acceleration of the block starting from that left-hand point is a constant 2 meters per second squared. Now, how we create that acceleration, that is not the business of this course, because you're only doing kinematics. Now, from elementary physics, you know that, or dynamics, you know that if this is the acceleration, the the velocity of it is the integral of 2, which is 2t, and the position of it is integral of 2t, which is t squared. So if for example, this length hypothetically is 20 inches, 20 inches, you can figure out how long it takes for the block to go from this end to the other end, and you get roughly 4.47. And if you plot the velocity, it's going to be linear. Constant acceleration gives you linear velocity. That's this dotted blue line. And the position is going to be parabolic, which is going to be your t squared, this red, red curve. Okay, and now we're going to model this thing in CATIA. First, we make a cartoon without any physics into it, which describes the motion. We make a cartoon basically, and then we put some physics into it, which tells you that the acceleration must be 2 inch per second squared. All right, then let's do it. Immediately, I'm going to save this thing, file, properties. I'll call it. What is that? I'll call it. Sorry, product. I'll call it the accelerating block. Actually, I'll call it the activity YY33 accelerating block. Okay, so we say okay. Immediately save it. File, save management. There we are, save as. On my desktop, I'll create a folder and I'll call it YY33. Okay. Good. We say okay. I'm going to change my units to inches. So tools, options. Let's see, parameters and measures. On the units, from millimeter, I'm going to switch it to inches. And then we say okay. Great. Insert the first part. Insert the new part in there, and that's going to be my track. So right-click properties. Properties. I'll call it track. And track. Say okay. And all it is a box which is 21 inches long and a width of 1, for example, and height, it really doesn't matter. But I'll do it exactly like the problem says. On that vertical plane, I will sketch a rectangle, like so. The width of it is 1. The height of it is irrelevant. Right now it is 1.8. I will also make it 1. Exit and pad this thing by 21 inches. Okay, so that's going to be the track. Now the block, I can put it on this side or I can put it on that side. I will put it on the other side. So there's a slight difference between the way I looks like here. Okay, so we're going to go insert all the way to the top, all the way to the top, insert new part, always say no, and I'm going to call this thing a block, right? Click properties, block, and block. Okay, let's make it. Double click on the block on that same plane, XY plane, and on purpose, this is on purpose, I'm going to draw it over there. Dimension, this is 1, and this is 1. Exit, pad it by 1 inch. All the way to the top, click on the floppy so that it saves everything in that folder. Now, as far as making the model, this is concerned, this is all done. Now we have to assemble. So I'm going to make the track stationary. Here is the fixed component. You select this, so the track is going to stay stationary, and this will move as I apply the constraints. So let me, let me bring this thing here and translate in the X direction. And in fact, on purpose, I'm going to rotate it like that. Okay. I don't know why I would do that, but I want to show you the constraints will work. So coincidence between this edge and that edge, okay? And coincidence between, for example, this side plane and that plane. Say okay. Okay. Now believe me, if I move this thing, if I move this thing and I say update, it'll go back to where it is. The only thing is that I wanted to start this thing from that end. So why don't I make a temporary constraint? So for example, this edge and that edge, update. And when I do that, then I'm going to delete it because I really don't need this thing to be part of my mechanism constraints or deactivate it, by the way. So all the way to the top, we are there, flop. Now we're going to go to the new part, which is creating the mechanism. So you go to start, uh, digital markup, VMU kinematics. Now I'm going to be using the magic wand to create the joint automatically. This is edge to edge, plane to plane. That's a prismatic joint. Okay. So I'll click on the on this magic wand, a new mechanism. Give it any name that you want. You can call it mechanism one if you want. You say okay, and auto create. So what happens is that the joints are created automatically. So let's go find out. Let's go find out. There better be a single degree of freedom joint, and it's a prismatic joint. The degree of freedom is 1. Joint is prismatic. Now, if you double click on this, notice that first of all, when you put the notice that this a prismatic joint is length driven. So if I make this thing 1, if I check this box,
you will notice that actually it tries to move in that direction, which is not what I want. I flip this arrow. Okay, now it goes this way. Arrow goes to the left. And it goes between minus 100 and 100. I don't have to change these things. I can leave it the way it is. But in reality, this is going to go from 0 to 21. But it really doesn't bother me. These things don't bother me because later on we're going to put some physics into the problem. We put the time in approximately 4.47 a second, which is never going to make this thing go past the 21-inch uh, limit. Okay. You want to make this thing 0 to 21? No problem. You want to do it like this? No problem, because we're going to set the time between 0 and 4 point, almost 4.7, and that's going to take you at most 21 inches. We say, okay, and this is your best friend. Mechanism can be simulated. Now, uh, notice that we have a command here. The command is that length limiting command, and we have we're gonna try to do that manually. There is the uh, simulation with command. You're in charge. Okay, so as I go to the right, this thing goes to the right. Of course, it goes by 100 inches. You can't even see it. Or as you go to the left, it'll take you to minus 100 and reset it. So we know that it works manually. Okay. Now, if you want to put some physics into this, and we're going to do that, you click on simulation with laws, not simulation with command, simulation with law. You click on it. What it says is that, listen, if you want simulation with laws, you must have defined some kind of a formula. You didn't do that. So we say, fine, I forgot to do that. We close on it. We close it. I'm going to click on f of x. See this knowledge toolbar? This knowledge toolbar is usually here. You bring it up, click on f of x. Now, I am not interested in everything in this model. This model has a lot of stuff in it. It's got dimensions of the bulb block, dimensions of the, track, etc. I'm interested only in the mechanism. You click on the mechanism, and there's only two things that are going to appear: kinematic, the time and the command. Okay? So the time, later on, we're going to go make it go between 0 and 7. The question is, what is the relationship between these two? So if you click, select this, select the command, and then you say add a formula. Select the command, add a formula. It says, oh, this thing, this length is equal to, well, what do I want this thing to be equal to? I want it to be equal to time squared. Okay, time squared. Uh, Remember, I showed you based on elementary physics, if the acceleration is 2 inches per second squared, then this thing is time squared. So we're going to say this is equal to uh, time. Now the time, what's the variable of time? How do you know what's the name of the time? You click on the time here. It's right there. Double click on it. It puts it there. So it's going to be star 2. There is the physics. However, it's the wrong physics. You'll see that because it's going to come back, say, wait a minute. Your left side of that equation is meters or inches. The right side is second squared. These can't be correct. So let's do that. We edit this. And what we do is, oops, sorry, don't edit it. Double click on it. So what we do, I will multiply this thing either in the front or at the end by 1 inch per second squared. So I can put it here, 1 inch underscore S. I think if we put S2 will work, we'll find out. Uh, Parentheses, just so that we don't get mixed up here. This, yeah, that should do, but I'd rather put a parentheses around it. Don't make your life harder, and then multiply. Okay, I could have written 1 inch underscore second squared and then times this. Okay, there, no more complaints. We say, okay, now we're going to do simulation with command. it says, okay, wait a minute. So do you want to go all 10 seconds? Well, 10 seconds will take you past the end of the link. So I'm going to say no, no. I'm going to go for roughly 4.47. 4.47. You say okay. Notice that this will go now from 0 to 4.47. There. Now we're going to play it. That's it. Play. Whoop. That's it. That's it. There's physics in it. The question is, how do I know? So let's go here. The only way for us to know is to be able to plot the position and acceleration and the velocity. We better get a constant acceleration, linear velocity, and a parabolic position. Okay, so we go back. We say, okay, the first thing we're going to do is to create some sensor. So here is a ball rolling down a ramp. See that? It says sensor, speed and acceleration. It's a speed and acceleration sensor, right? You click on it. It says, okay, what is your reference product? See that? Reference product is the track point that we want to plot something about. I'm going to select this point or that point or that point or that point. We say, okay. So we did create some speed and acceleration sensors that we can later go and plot. So let me go ahead and click on the simulation with laws, activate sensor. It says, okay, what do you want to recover from this motion? Well, first of all, this is direction X. I want to know the position, X vertex position. See how it turns from no into yes? I want X linear speed. So velocity in the X direction. See how it becomes yes? And acceleration, linear acceleration, direction X. Okay? Became yes. Now, you move this thing out of the way. Don't close it. You move this thing out of the way. Okay, so let's play it. It reaches there. Now, when you are done here, you move this thing up and then you say graphics. So it will give you the acceleration, you ask for it, velocity, you ask for it, and position, you ask for it. The only thing is that these units are not correct. Should be inch per second squared, etc. So we're going to say no problem. Close that. Okay. Let's see if we do the units, it'll take it here. So we go to tools, options. For velocity, you can sort this out alphabetically by clicking on magnitude. So let's see if we can find velocity here. Velocity. We're going to make it inch per second square, inch per second. And acceleration. Once again, click on magnitude to sort it. Sort it. Where is acceleration? Right there. Um, uh, what is that? Inch per second squared. We say okay. Okay, let's go back to simulation with laws. Rewind it. Activate sensor. Move it down. If there is anything in the history, clear it. There is none here, which is good. Move it down. Play it. Move it up. Graphics. There we are. You see, the units are inch per second squared. For acceleration is inch per second squared. For velocity, inch per second. Position is inch versus time. Now, you have to capture this image and save it as a JPEG file or put it in a Word document, because we will ask you to submit these kind of plots, and there is no way to make it stay when you submit your work on the midterm, on the final. There's no way for me to be able to get this thing. So what I'm going to do is this. Uh, s- saving, capturing this is function, my at least computer function, print screen, this, okay. And can I save this thing? Nope. So I get a Word document. There we are. Paste. Okay. And let's save this thing. File. Save as. Like that browser. Desktop. And there was a folder that we did. What do we call it? Accelerating block. Uh, Activity. There's the activity. My generated plots. Generated plots. Okay. So this is insert. Actually, this is Word, right? So we say that uh, velocity, acceleration, and position plots. Okay, good. Now suppose I also want velocity versus acceleration. Now, velocity versus acceleration, you think about it. Acceleration is always a constant. Velocity versus acceleration is going to be just or let me do it differently. Acceleration versus velocity. Acceleration versus velocity. Acceleration versus velocity is just going to be a horizontal line, just like that. But I want to generate it. So we go here, we close that. We're going to say options, customize, add. You can call this thing curve one or acceleration versus velocity. So we go acceleration in the x direction. So that's abscissa is x-axis. So acceleration, so that's going to be x linear speed versus acceleration. And then we say okay. Graphics. Click on the graphics. There we are. Once you close it, you click on the graphics, and it's needless to say, you're going to get a constant curve. Acceleration versus velocity. Abscissa, ordinate. Okay, and then you save this thing. So you're going to say function uh, print screen. Here's my Word document. Home paste. This is acceleration versus velocity. Make sure I can see your scale. Good. Close it, close it, close it, close it, and save. Okay, so if you go to that folder, there is activity, there is your product, here's the track, here's the block, and here's the Word document that you created, and I can mark uh, your midterm and final. Okay, these are critical. Without these, there is no way for me to know whether you have done it or not. So these cannot be recorded in the tree. Okay, good luck.